Welcome back, students. In the past couple of lectures, we've been discussing probability, and we've only been considering pretty simple systems such as flipping coins, rolling dice, and those sorts of things. Our goal for today is to extend the basic concepts of probability that we discussed in the past couple of lectures to more complex systems and molecular systems in particular. At the end of the lecture, we're going to begin to derive the Boltzmann distribution, and we'll finish this off in the next lecture. So today we'll be talking about the functional form of the Boltzmann distribution. We're pretty comfortable with the Boltzmann distribution itself, having the form of e to the negative energy over kT. We've used it in the last semester, but we're going to see why that is the case, how the energy relates to temperature in that way. And we'll do this both in today's lecture and in the following one. So the learning goals for today are going to be to think about chemical systems as distributions of microstates. We'll talk about what we mean with microstate here in a bit. Then we're going to calculate the weight of a microstate. This is going to be very similar to when we were calculating the weight of a different distribution when we're doing something as simple as flipping coins. And then finally, we'll start to derive the Boltzmann distribution and actually use it to calculate the probability of observing a particle at a particular energy level. So we're going to go and think first about the simple case of flipping 4 coins. With this, we were able to pretty easily calculate the likelihood of getting a certain number of heads. So for example, to get 2 heads, we can see that there are 6 outcomes that correspond to 2 heads. If we counted them up there would be a total of 16. So we have an overall 6 out of 16 chance, which is like 37%, of getting 2 heads out of 4 coin flips. Now, for this, we simply were able to count. We could count the number of configurations or microstates that came with 2 heads, and then we could count the total number of configurations or microstates to get this chance. We can't really do that for molecular systems, but we can calculate the weight of a certain microstate. Now, in this case, we also could calculate the total weight. It's not something we can do very easily for chemical systems, but remember, again, the actual total weight doesn't really matter. So if I look at this, I can use the total weight to get a percent, but the percentage chance of getting 2 heads is always going to be 6 times 0 heads. And that's simply because the weight of 2 is 6 times greater than the weight of 0. So I don't actually really need to know the total weight or the percent to figure out how much more likely I am to get 2 heads than 0 heads. So here's some of the things that we've been talking about. We can get this easily with coin flips. For molecular systems, there's not just 0, 1, 2, 3, or 4 heads. Molecular systems have more going on than just these sorts of number of heads. They also have, in particular, energy. And we know from previous discussions, as well as our intuition, that molecules don't have equal likelihoods to be at equal energy levels, at least for all of their degrees of freedom. So for something like translation, maybe that's not true. But for vibration and rotation, there's significant chances to be at these different energy levels. So we have to consider the energy of a system in order to figure out what sort of configurations or microstates it can populate. We've been talking a lot about configurations and microstates. The configuration here is the arrangement. So here for 2 heads, the 2 heads configuration is 2 heads and 2 tails. Each of these possibilities here is a microstate. In molecular systems, just like in things like coin flips, we often don't really care about the microstate and are more interested in the overall configuration. Now, we'll use the central postulate here of statistical mechanics to help us out, and that is that every possible microstate of an isolated assembly of units or an isolated system occurs with equal probability. So in that case, we're just as likely to get 0, 0, 0, 0, or tails, 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 as we are to get heads, 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 as we are to get tails, tails, heads, heads. And that's the same as we use for regular probability as well. Now, how do we actually apply this to molecular systems? We're going to go and consider a case of 3 quantum mechanical harmonic oscillators. To consider what's going on with our three harmonic oscillators, we have to go back into our memory and grab the energy levels for the quantum mechanical harmonic oscillator. You'll recall from last semester that the energy levels depended on the quantum number n, and they were simply h nu, where h was Planck's constant and nu was a vibrational constant, times the quantum number n plus 1/2. And we'll more often write this in terms of spectroscopic units. So rather than using the nu as a frequency in per second, we'll use it in inverse centimeters. And we have h, Planck's constant, times the speed of light in centimeters, times nu, which is now a vibrational constant in inverse centimeters. And then we have n plus 1/2. Now, I won't justify this today, but I'll justify it in the future. It turns out, and you might be familiar with this idea, is that energy is really only dependent on a difference, right? So even though these quantum mechanical harmonic oscillators have a 0-point energy, it's often easier to ignore that 0-point energy. And we'll justify this in a couple lectures, so if you're disturbed, don't worry too much about this. I will justify this assumption to you. And it just makes things a little bit easier to consider when we have a 0 in terms of energy, but we don't actually need it, but it just makes the math a little bit easier. So now what we want to do is consider a system with 3 quantum mechanical harmonic oscillators. And what we're going to do is say this system has 3 quanta of energy. What's a quanta of energy? Well, a quanta of energy is simply hc nu. So we have 3 hc nu worth of energy. And we have 3 quantum mechanical harmonic oscillators to put this energy into. So what kind of options do we have? Well, what we could do is write a simple diagram here. So we'll put energy on this y-axis. We'll have a 0 energy. We'll have 1, 2, and 3. And this is all energy in terms of hc nu. Since we have 3 quantum mechanical harmonic oscillators, what are our options? Well, we have one option where the energy goes into each harmonic oscillator, and each harmonic oscillator has 1 quanta of energy. That's one outcome. And we can only have 1 microstate that corresponds to that configuration. We also have an outcome where we put 1 at 0, 1 at 1, and 1 at 2. We actually have some more ways to arrange this. So I could do it in this way as I have it here, or I could do it in a different way. I could say we have this one at 0, this at 2, this at 1, and we can continue. We could have 1, 0, 2, 2, 0, 1, because I have these 3 different harmonic oscillators. So I have only 1 microstate that corresponds to the 1 to 1 to 1, but I have 6 microstates that corresponds to having 1 at energy 0, 1 at 1, and 1 at 2. And now I'm running out of space here on my screen, but there are 3 more that we can do, and those have 1 at or 2 at 0 and 1 at 3. And since I have 3 oscillators, I could do either one of those being at the 3 state. So I have 3 different states. So in this way, I could pretty easily calculate my likelihood of being in any of these states. I have a 1 out of 1 plus 6 plus 3 is 10. So I have a 10% chance of being in this configuration, a 60% chance of being in this configuration, and a 30% chance of being in this configuration. So I am most likely, in the case of 3 quantum mechanical harmonic oscillators with 3 quanta of energy, to observe this configuration, where I have 1 oscillator with 2 quanta of energy, 1 with 1 quanta of energy, and 1 with 0 energy. I'm still pretty likely to get all of these because I have an overall very small number of objects. In this process, we have used the brute force method, whereby simply plugging in all of our options, we've found the total number of microstates that are possible, as well as their relative weights. Now, this becomes untenable for any large number of molecules and energy. Now, this is even true if our numbers were like 5 or 10. We couldn't really do this brute force method if we had 10 harmonic oscillators and 10 quanta of energy. So what do? We need to calculate the weight. And we can actually calculate the weight in a pretty much a direct extension from what we did for coin flips. So for coin flips, the weight of a configuration was simply equal to n factorial over j factorial times n minus j factorial. Now, what this is, n factorial on the top is the total number of coins, j is the number of heads, and n minus j is the number of tails. So what we're doing is we're taking the number of our coins factorial divided by the two options that we had, heads and tails. Now, in our energy distribution, we don't have only two options. In fact, we have 4. We have 0 energy, 1, 2, or 3. And it turns out that we can basically do the same thing that we did with heads and tails. We can say that the weight is equal to, in this case, we use an uppercase n, but it means the same thing, the total number of molecules that we have divided by a 0 factorial, a 1 factorial, a 2 factorial, a 3 factorial. In general, what we can say is that the weight is equal to n factorial over capital pi, where this capital pi is a product of all of our lowercase a sub n's. And these lowercase a sub n's are simply the different groups that our molecules can be in. So if we wanted to calculate the weight of our distributions above, we can say that the weight of our first distribution, if we call this distribution 1, this one 2, and this one 3, the weight of distribution 1 is n, the total number of objects, that is 3 factorial over 0 factorial, 3 factorial, 0 factorial, 0 factorial. That's 6 over 6, which is 1. The weight of the second distribution is equal to 3 factorial. Now it's 1 factorial, 1 factorial, 1 factorial, 0 factorial. That's 6. And the weight of the third is simply 3 factorial over 2, 0, 0, 1, 4, 3. And you can see that these numbers match the numbers from the brute force method. If we wanted to, we can convert these weights into a probability by simply dividing by the total weight. There's no convenient way to get the total weight like there is for coin flips, so we actually have to add it up. The total weight then is simply 1 plus 6 plus 3 equals 10, and we can convert these weights into a probability if we would like to. For this very simple example, all 3 configurations have a substantial likelihood of occurring. However, as the number of particles increases, say to Avogadro's number, the weight of one outcome increases relative to the others. This happens to such an extent that it becomes the only distribution that could be observed. We call this distribution the dominant distribution, and in some cases, the Boltzmann distribution, like you've been familiar with hearing that from last semester. Since any molecular system contains at least a quadrillion molecules, so for reference, 1 quadrillion is 10 to the 15th, which ends up being 16 nanomoles, the dominant distribution will be extremely sharp. How can we define the dominant distribution? What we need to do is simply find the peak of the probability distribution function. So our function would look something like this. Well, there will be a sharp peak, and that will be the dominant distribution, is whatever has the largest weight. Now, for the purposes of our examples, we're more likely to be considering the natural log of the weight, because the weight is probably going to be a very large number for any substantially sized system. And what we have on the x-axis here is some configurational index, and we'll define that a little bit later on. So with this setup in mind, the Boltzmann distribution, the dominant distribution, corresponds to this maximum here. And that is simply the configuration at which the derivative of the natural log of the weight with respect to the configuration is equal to 0. Since the weight is in general a very large number, we can evaluate the natural log of the weight using Stirling's approximation. So this will say that the natural log of weight is equal to the natural log of n factorial over the product of all of our a sub n factorials, which is then the natural log of n factorial minus the natural log of the product of all of our a sub n factorials. Now, this is going to be the natural log of a 0 factorial, a 1 factorial, a 2 factorial, and so on. And so since we have the natural log of a product, we can make that rather a sum of natural logs. So that we have the natural log of n factorial minus the sum of the natural log of the a sub n factorials. Now, here comes Stirling's approximation. So we'll say that the natural log of the weight is n natural log n minus n. And then we're going to have a sum of a sub n natural log a sub n minus a sub n's. And we can separate this sum out here. So we'll have n natural log n minus the sum over n of a sub n natural log a sub n plus the sum of a sub n. Now, what we can do here is recognize that the sum of a sub n is simply equal to n. How can we do that? Well, consider what these a sub n's are, right? These are the total number of all of the options that we have. So for the coin flip, the a sub n's would be heads or tails. If we have 10 heads and 10 tails, we have flipped 20 coins. And they're related in this way. So with this, we can see that the sum of all of our a sub n here is positive n. That cancels with this negative n, and we can remove those. So therefore, the natural log of weight is simply n natural log of n minus the sum of over n of our a sub n natural log of a sub n. Now, at this point, we're choosing our configurational index here, and we're going to choose a sub n, which represents our occupation numbers. We do this because our goal is to figure out the occupation numbers that the molecules have in the dominant distribution. So what we want to evaluate then is the derivative of the natural log of weight with respect to a sub n. And then we need to take the derivative of our equation up here, our n natural log of n minus the sum over n of a sub n natural log of a sub n. So it's pretty easy to take the derivative of a sub n natural log of a sub n with respect to a sub n, but what about n natural log of n? Well, remember that n is simply equal to the sum of all of our a sub n's. So if we're taking the derivative of a sub n with respect to a sub n, if n is equal to a 0 plus a 1 plus a 2, and we're taking the derivative with respect to, say, a1, we simply get 1. If it's a2, it's 1. If it's anything, we get simply 1 there. So we can evaluate both of these pretty easily. So the derivative of n natural log of n, we do the product rule. The derivative of n with respect to a sub n is 1. So we'll get the natural log of n then, and then we do plus n times the derivative of the natural log of n, and that's going to be 1 over n. And we can do the same thing for the other side. That'll give us minus natural log of a sub n, and then we also have minus a sub n, and then we're going to have a 1 over a sub n. So these will both give us 1. They'll cancel out. And our derivative of the natural log of the weight with respect to a sub n is simply the natural log of n minus the natural log of a sub n, which is equal to the negative natural log of a sub n over n. At this point, you might expect us to then set the natural log of a sub n over n equal to 0, like we wanted to do up here, and use that to solve for the dominant distribution. However, we need to introduce another piece of information. The occupation numbers are not independent. If my system contains a certain amount of energy, I can't simply change the occupation numbers. If I add 1 unit of energy to one molecule, that energy must come from another. I need to take that unit of energy away from a different molecule. So we have 2 extra conditions in addition to this that we must satisfy. Those conditions that we need to satisfy are that the sum of the change in occupation numbers is equal to 0. So we can't make or lose any molecules of the system, and also the sum of the energy levels times the occupation numbers, the change in occupation numbers equals 0. So we have conservation of matter and conservation of energy in these two conditions here. We can incorporate these two factors by including Lagrange multipliers. This allows us to maximize a function with respect to multiple variables that are constrained amongst themselves. And so to do that, what we'll do is write that the derivative of the natural log of the weight is equal to the sum of the negative natural log of a sub n over n. So this is our initial condition. And then we'll have dA sub n here. So this is kind of what we were starting with. And then we'll include these Lagrange multipliers, which will come into coefficients alpha and beta. So then we'll add alpha times our other condition here. And then we'll subtract, in this case, beta times our second condition here. And now all of these things must equal 0. So we can group all of these things in the same sum and have that we have a sum over n of the negative natural log of a sub n over n plus alpha minus beta epsilon n, and then we have DAN. And this is what needs to be set equal to 0 in order to find the dominant distribution. So we can say finally that 0 is equal to the negative natural log of a sub n over n plus alpha minus beta epsilon sub n. With this equation, we can rearrange and solve for a sub n. So what I'm going to do is add the natural log of n term over. So we get the natural log of a sub n over n is equal to alpha minus beta epsilon n. We'll raise this to e, so that will give us a sub n over n is equal to e to the alpha minus beta epsilon n. Using exponential properties, we can separate these into two exponentials. So we'll have this being e to the alpha times e to the minus beta epsilon n. And then we can multiply through by n to get a sub n is equal to n e to the alpha e to the minus beta epsilon n. From here, we can recognize that n is simply the sum of all of the lowercase a sub n. We've already used that before in this derivation. So we can say that n is equal to the sum of all of the a sub n's, which is then equal to the sum of n e to the alpha e to the minus beta epsilon n. Now, n e to the alpha are not dependent on lowercase n, so we can pull them out of this sum here for the following expression. Now we can cancel out both of these, and we can rearrange to get a measure for what e to the alpha is. In this case, it turns out that e to the alpha is simply 1 over the sum of e to the minus beta epsilon n. And for simplicity, we'll say that e to the minus beta epsilon n, when you sum all those together for all of the n's, that is q, which we'll call the partition function. Why does this matter? Why have we gone through the process of doing all of this? Well, let's consider what our goal was, right? Our goal is to figure out what the most likely distribution is. And now what we have is something that reflects n, right? So for example, if we wanted to know what the probability of observing a molecule at a certain energy level is, well, that would simply be the number of molecules at that energy level over the total number of molecules. Well, look at this here. We have now an expression for a sub n over n. So a sub n is equal to n e to the minus beta epsilon n. And we know that e to the alpha, we can define that as 1 over q, or 1 over the sum of all of the e to the minus beta e sub n. So at this point, this should probably look very familiar to you because we are dangerously close to deriving the complete Boltzmann distribution. So this equation says if we want to find the probability of having a particle at a certain energy level n, we simply need to take that energy level, multiply it by beta, and as yet we don't know what beta is, but you'll probably be able to guess that it's simply 1 over kT, and we'll derive that in the next lecture. So we take this e raised to the some constant times our energy level and divide that by the sum of all of these for every energy level, and that is the probability that we will observe a molecule at that energy level. And that is pretty remarkable. So what do we do with this? Well, without even resorting to having beta being kT, we'll do that in the next lecture. What we can do is have a system. So say we have our three energy system. We have E0 equals 0, E1 equals 1 over beta, and E2 is 2 times 1 over beta, or 2 over beta. What's going on with this system? Well, we can calculate the likelihood of being an energy level 0, 1, or 2. So energy 0, so n is 0, En is equal to 0, then we have 1 over beta, then we have 2 over beta. What is the e raised to this number? So e to the minus beta En, we can evaluate that. For 0, that's simply e to the 0 is equal to 1. Here, this is going to be e to the minus 1, which is equal to 0.37. And here it's e to the minus 2, which is equal to 0.14. If we want to convert this into a probability, these numbers alone are actually probability enough. So the fact that this is 0.37 and this is 1 means we are approximately 3 times as likely to observe something in the ground state as the first excited state in the system. If we want to see that a little bit easier, we can convert it to a percent, but we need to know what Q is. In general, Q gets smaller and smaller as n gets larger and larger, and you can see that here since we have e to the minus n essentially. We can actually use a Taylor series here. So our trend is e to the 0, e to the minus 1, e to the minus 2. So we can say our partition function is equal to the sum of n equals 0 to infinity of e to the minus n. And this is equal to 1 over 1 minus e to the minus 1, which is 1.58. So dividing these numbers by 1.58, we can convert them into a percentage. And for that, we get 0.633, 0.233, and 0.086. This is a little bit different than what we've done last semester. So last semester, we were primarily interested in the likelihood of being in, say, the excited state compared to the ground state. So what we evaluated was essentially e to the minus beta E1 over e to the minus beta E0. And you can see that that's going to be the same number, whether or not you do that in a percentage over here or this term right here. So we didn't actually ever have to go into the partition function. But if we want to know a percentage, we need that partition function in the denominator. And we're essentially doing the same thing as we did last semester. I just briefly want to mention degeneracy at the end here. Some terms in quantum mechanics are degenerate, which means there are multiple terms that have the same energy level. We can pretty easily account for these. So some of these include rotational energy levels are degenerate, and also things like p and d orbitals are degenerate since they're based on the rotational energy levels. We can account for this by simply adding it in to our system here. So for example, if our n equals 1 level was actually twofold degenerate, what that would mean is that there are 2 energy levels that are n equals 1. And what that would do is change the likelihood of being at that level, since there's twice as much of them, and also change the total partition function, since there's more energy levels to be involved in. So we can simply add to our partition function e to the minus 1 if there is an extra energy level at e to the minus 1, which would give us 1.95 for our partition function. And then what we would do is there would be 2 of these e to the minus 1 levels. And so it would be twice as likely to be there. So with this, we can go get different percentages. We'd find out that the new probability, if we had this extra energy level, would be 0.513 for the ground state, 0.377 for the first excited state, and 0.069 for the second excited state. We'll continue going through this in the coming lectures. So in the next lecture, we'll look at what beta is. And then in the following lectures, we'll go through and actually try to apply this to some different real quantum mechanical systems, such as translation, rotation, vibration, and so on. And hopefully we'll have plenty of time in class to do a lot of examples, so we can really get our feet wet and understand how this math and these processes work.